Welcome to Chapter 1 of our Chemical Engineering Thermodynamics series, Energy and the First Law. The subtitle tells you where we are going, state functions, balances, and why thermodynamics runs the plant. Our Chemical Engineering Introduction series ended twice at the same wall. Its Chapter 1 wrote balances and observed that the energy balance usually decides whether a process is worth building, without ever saying where stream energies come from. Its Chapter 2 warned that no catalyst can push a reactor past chemical equilibrium without saying what sets that limit. Thermodynamics is what lies on the other side of both. Across these 10 slides, we build the foundation: what a system is, why state functions make energy bookkeeping tractable, and how the first law turns into the energy balances that decide what a process costs to run. By the end, you will be able to apply the closed system and steady flow forms of the first law, separate sensible heat from latent heat, and compute a heat exchanger or reboiler duty from a flow rate and a phase change. Thermodynamics answers 3 questions that no rate law can touch. First, how much energy does a transformation require or release? Kinetics tells you how fast a reaction runs. Only thermodynamics tells you how much heat you must add or remove while it does. Second, how far can it go? Equilibrium is a thermodynamic limit. A better catalyst reaches it sooner. Nothing takes you past it. Third, which direction is spontaneous? Whether a process runs by itself or has to be driven, and at what minimum cost, is decided by the second law, which is Chapter 2. That gives us the division of labor worth memorizing. Kinetics governs rate, thermodynamics governs possibility and price. The practical consequence is asymmetric and worth pausing on. A design that ignores rates is merely slow, and you can usually fix it with a larger reactor or a better catalyst. A design that violates thermodynamics cannot be built at all, and no amount of engineering effort will rescue it. That is why thermodynamics gets checked first. Every thermodynamic statement begins with a choice. What are we accounting for? The region selected is the system, everything else is the surroundings, and the imaginary surface between them is the boundary. That boundary is chosen by the engineer, not given by nature. Draw it around one heat exchanger and you get its duty. Draw it around the plant and you get the site utility bill. Systems are classified by what the boundary lets through. Open systems pass both mass and energy, which covers pumps, reactors, heat exchangers, and columns, so most of a plant. Closed systems pass energy but not mass, like a sealed batch vessel. Isolated systems pass nothing, an idealization used for reasoning. Now the most useful distinction in this chapter. State functions, such as internal energy, enthalpy, temperature, pressure, and volume, depend only on the current state. Path functions, heat and work, depend on how the system got there. Because a change in a state function can be computed from tables without knowing the path, steam tables and process simulators are possible at all. The first law of thermodynamics is conservation of energy with heat and work counted honestly. For a closed system, delta U equals Q minus W. The sign convention must be stated explicitly, because textbooks differ. Here, as in most chemical engineering practice, Q is positive when heat flows into the system, and W is positive when work is done by the system on the surroundings. Heat in raises internal energy, work out lowers it. Most plant equipment is not closed, though. It flows. For an open system at steady state with one inlet and one outlet, neglecting kinetic and potential energy terms, the working form is delta H equals Q minus shaft work. The reason enthalpy appears instead of internal energy is that flowing material carries its own pressure-volume energy across the boundary, and enthalpy bundles that in by definition. H equals U plus PV for a heat exchanger, a reboiler, or a condenser. There is no shaft work at all, and the equation collapses to the most used expression in process engineering. Q equals delta H. Let's put numbers on it. Take 1 kilogram of liquid water at 25 degrees Celsius and turn it into saturated steam at 100 degrees Celsius and 1 atmosphere. The path splits into 2 physically distinct steps. Step 1 is sensible heat, warming the liquid. Using a specific heat capacity of about 4.18 kilojoules per kilogram per Kelvin, the heat is mass times heat capacity times temperature change. 1 times 4.18 times 75, which gives 313.5 kilojoules. Step 2 is latent heat, boiling it at constant temperature. Using a latent heat of about 2257 kilojoules per kilogram, that step costs 2257 kilojoules. The total is 313.5 plus 2257, which is 2570.5 kilojoules. Now look at the split. The vaporization step costs about 7.2 times as much as heating the liquid through those 75 degrees, and it happens at constant temperature, so a thermometer reports nothing at all while the great majority of the energy goes in. That ratio is the reason evaporation and distillation dominate plant energy budgets. Boiling is where the money goes. Specific heat capacity is the energy needed to raise 1 kilogram of a substance by 1 Kelvin at constant pressure. It is a material property, mildly temperature dependent, and for hand calculations, an average value over the range is normally good enough. Compare a few classes of material. Liquid water sits near 4.18 kilojoules per kilogram per Kelvin, with a latent heat of 2257 kilojoules per kilogram at 100 degrees Celsius and 1 atmosphere. Organic liquids run about 1.5 to 2.5, with latent heats of roughly 300 to 900 kilojoules per kilogram. Gases are of order 1. Liquid water is a conspicuous outlier, roughly twice the heat capacity of a typical organic liquid, which is why it is both an excellent coolant and an expensive thing to boil. The pattern across the table is the practical rule of this chapter. Phase changes are expensive, and temperature changes are comparatively cheap. Heating an organic liquid through a large 50 Kelvin span costs perhaps 75 to 125 kilojoules per kilogram. Boiling it costs several hundred. On a flow sheet, the first law becomes an arithmetic you can do on the back of an envelope. For a stream of a given mass flow rate, with no phase change, the heat is the mass flow rate times the heat capacity times the temperature change. With a phase change, it is the mass flow rate times the latent heat. The result, called the duty, is the required heat rate in kilowatts or megawatts. It sizes the exchanger, it sets the steam or cooling water flow, and it lands directly on the operating cost line. This is why a distillation column's reboiler and condenser are usually the largest utility consumers on a flow sheet. A column does not merely warm its feed. It boils a stream at the bottom and condenses it again at the top, repeatedly, because the reflux return to the column must be vaporized once more on every pass. Multiply a latent heat of hundreds or thousands of kilojoules per kilogram by that reflux-amplified internal flow, and the column dwarfs the pumps, the preheaters, and often the reactor itself. The chapter's code example makes the point quantitatively. It sweeps the feed temperature and splits the duty of making saturated steam at 100 degrees Celsius into its sensible and latent parts. Feed at 20 degrees needs 334.4 kilojoules per kilogram of sensible heat plus 2257 of latent heat, a total of 2591.4. So the latent term supplies 87.1%, a ratio of 6.75. Feed at 25 degrees gives 313.5 plus 2257, or 2570.5, and 87.8%. At 40 degrees, sensible heat falls to 250.8, and latent heat is 90%. At 60 degrees, 167.2 and 93.1%. At 80 degrees, only 83.6 kilojoules per kilogram of sensible heat remains, and latent heat is 96.4% of the total. Now read what that says about feed preheating. Raising the feed from 20 to 80 degrees removes 250.8 kilojoules per kilogram from the boiler's job, which is real money. But 2257 kilojoules per kilogram of it never goes away. Preheat all you like. The phase change is untouched. Step back to why this chapter is titled the way it is. The Chemical Engineering Introduction series observed that the energy balance, not the mass balance, usually decides whether a process is worth building. This chapter is where that claim finally gets its arithmetic. Once you can compute a duty, you can price a process, and pricing is what design decisions actually turn on. There is an obvious question waiting here. In a distillation column, the condenser rejects almost as much energy as the reboiler supplies, so why not feed one with the other? Sometimes you can. Heat integration and multi-effect evaporation do exactly that. But the limit on how much can be recovered is not a first law limit. The first law counts energy and finds it conserved. It never says that heat rejected at 40 degrees Celsius is worth less than heat supplied at 150 degrees Celsius. That accounting, the one saying energy has quality as well as quantity, requires entropy, and that is where we go next. Let's pull the chapter together. Thermodynamics answers 3 questions kinetics cannot: how much energy, how far, meaning equilibrium, and which direction, meaning spontaneity. Kinetics governs rate, thermodynamics governs possibility and price. Analysis starts by drawing a boundary. Open systems exchange mass and energy, closed ones only energy, isolated ones neither, and plant equipment is overwhelmingly open. State functions depend only on the current state, while path functions, heat and work, depend on the route, which is why enthalpy changes can be read from steam tables. The first law for a closed system is delta U equals Q minus W, with Q positive into the system and W positive by the system. At steady flow, it is delta H equals Q minus shaft work, where H equals U plus PV heating 1 kilogram of water from 25 degrees Celsius to saturated steam at 100 takes 313.5 kilojoules of sensible heat plus 2257 of latent heat, or 2,570.5 kilojoules, the latent term being about 7.2 times the sensible one. Next chapter: Entropy and the second law. Welcome to Chapter 2 of Chemical Engineering-Thermodynamics. Chapter 1 gave us a ledger. Energy is conserved, and we can count it. This chapter gives us a compass. The first law audits quantity, but it never tells you which way a process will actually go on its own. The second law does. Across these 10 slides, we will do 4 things. First, see why energy conservation alone cannot predict the direction of a process. Second, define entropy as a state function and state the second law as the entropy of the universe never decreasing. Third, use that law to derive a hard ceiling on how much work any engine can extract from heat, the Carnot efficiency, and see why work is thermodynamically more valuable than heat. Fourth, apply exactly the same reasoning to separation, computing the minimum work needed to unmix a mixture, and comparing it with what real distillation columns actually consume. We finish with Gibbs energy, the single criterion that carries us into chapters 3 and 4. Drop a hot steel block into cold water. Heat flows from the block into the water until both reach the same temperature and energy is conserved. Now imagine the reverse. The water spontaneously cools while the block heats up. Energy would be conserved just as exactly. Nothing in the first law forbids it, and yet it never happens. The same asymmetry is everywhere in a plant. Stir ethanol into water and you get a solution, but the solution never separates itself back into 2 layers. A gas leaks from a cylinder into a room, but it never crowds back into the cylinder. Every one of these processes conserves energy in both directions, yet only one direction is ever observed. The first law is a bookkeeper. It audits quantity, but it says nothing whatsoever about direction. Something else is doing the choosing, and that something is the second law of thermodynamics. The quantity it tracks is entropy. Entropy, given the symbol S, is a state function with units of joules per Kelvin. Like internal energy or enthalpy, it depends only on the current state of a system, not on how the system got there. For a reversible transfer of heat at constant absolute temperature T, the entropy change equals Q reversible divided by T. The temperature in the denominator carries the physical meaning. The same joule of heat produces a larger entropy change when it enters a cold body than when it enters a hot one. That is exactly why the hot block heats the water and not the reverse. The entropy the block loses at high temperature is smaller than the entropy the water gains at low temperature, so the transfer increases the total. Statistically, entropy counts possibilities. A macroscopic state that can be realized by an enormous number of molecular arrangements, called microstates, is overwhelmingly more probable than one realizable in only a few ways. Entropy is the logarithm of that count. The second law states it compactly. The entropy change of the universe, which is the entropy change of the system plus the entropy change of the surroundings, is greater than or equal to 0. Read that carefully because it is often misquoted. The entropy of a system can certainly fall. A refrigerator freezes water every day, but it can only fall if the surroundings gain more entropy than the system loses. Equality holds only for a reversible process. An idealization runs so slowly and so free of friction, unrestrained expansion, finite temperature differences, and mixing that it could be retraced exactly. No real process qualifies. Every real process generates entropy, and that generated entropy is destroyed work potential. This is the point to carry into your engineering career. Generated entropy is the thermodynamic name for the money a plant loses to irreversibility, and it appears on the utility bill every single month. The most consequential result of the second law concerns converting heat into work. A heat engine takes heat from a hot reservoir at temperature TH, produces work, and must reject some heat to a cold reservoir at temperature T. See, that rejection is not an engineering failure to be designed away. It is what keeps the total entropy from decreasing. Requiring the entropy of the universe to be greater than or equal to 0 gives a hard ceiling on efficiency. Eta maximum equals 1 minus Tc divided by Th, with both temperatures absolute in Kelvin. Take a steam power plant with a boiler at 500 degrees Celsius and cooling water at 25 degrees Celsius. That is 773 Kelvin and 298 Kelvin, so eta maximum is 1 minus 298 over 773, which is 0.614, or 61.4%. No boiler design, working fluid, or turbine metallurgy can beat that. Real steam plants land well below it, typically in the 35 to 45% range. The engineering lesson runs deeper than power generation. Heat and work are both measured in joules, but they are not interchangeable. Work converts to heat completely and freely, while heat converts to work only partially, and the fraction shrinks as the source gets colder. So rank them. Work, meaning electricity, shaft power, and compression, has high thermodynamic value because it is fully convertible, which makes it expensive. Buy as little of it as you can. High-temperature heat from a fired heater or high-pressure steam has moderate value and is worth cascading down to lower-temperature duties. Low-temperature heat, low-pressure steam, or warm water has low value. It is nearly worthless for work, though still useful for heating. Two plant realities follow directly. Heat integration matters, and pinch analysis is the scheme for it. And compressors dominate operating cost wherever they appear, because they consume work and no amount of waste heat can substitute. Now apply exactly the same logic to the plant's other great energy consumer. Mixing is spontaneous because it increases entropy. A mixture has vastly more microstates available to it than the separated components do, so mixing is simply what almost all arrangements look like. But if spontaneous mixing raises entropy, then unmixing must lower it, and by the second law that can only be paid for with work brought in from outside. This is why separation is never free, and why no equipment, however clever, can beat the thermodynamic minimum, though better equipment can close the gap toward it. For an ideal binary mixture of mole fraction x, the entropy of mixing per mole equals minus r times the quantity x times the natural log of x, plus 1 minus x times the natural log of 1 minus x. The minimum reversible work needed to undo that mixing at temperature T is simply that entropy multiplied by T, that is the number we compute next. So write the minimum work as W minimum equals minus RT times the quantity x times log x plus 1 minus x times log 1 minus x, take an equimolar mixture at 298 Kelvin, with R equal to 8.314 joules per mole Kelvin. The bracket for a 50-50 split is 0.693, so W minimum equals 8.314 times 298 times 0.693, which is 1717 joules per mole, about 1.72 kilojoules per mole. The curve is symmetric and peaks at x equal to 0.5, so a 50-50 mixture is the hardest to separate. A 10% mixture costs only 805 joules per mole of mixture, though a great deal per mole of the trace component recovered. Now the comparison that should stay with you. Published analyses report that real distillation consumes on the order of 10 to 100 times the thermodynamic minimum. That headroom is why heat pumps, dividing wall columns, and membranes are such active research targets. Tracking the entropy of the universe means accounting for the surroundings, which is awkward in practice. Fortunately, chemical engineers almost always work at constant temperature and pressure, and for those conditions, the second law repackages into a property of the system alone. The Gibbs energy, G equals H minus T s its power, is the criterion it yields. At constant temperature and pressure, if delta G is less than 0, the process is spontaneous in the direction written. If delta G equals 0, the system is at equilibrium, with no net change. If delta G is greater than 0, the process is non-spontaneous, and the reverse direction is the spontaneous one. Read the definition as a competition. The enthalpy term rewards lowering energy, forming bonds, condensing, ordering. The minus Ts term rewards raising entropy, breaking bonds, vaporizing, mixing. Temperature is the referee, and raising it strengthens the entropy side. That is why a liquid boils when hot and freezes when cold. Let's pull the chapter together. The first law audits energy quantity but permits both directions, and the second law supplies the direction. Entropy S is a state function, equal to Q reversible over T for isothermal reversible heat transfer, and statistically it counts the microstates available to a state. The entropy of the universe is greater than or equal to 0, with equality only for idealized reversible processes, so every real process generates entropy and destroys work potential. Carnot gives eta maximum equal to 1 minus Tc over Th with absolute temperatures. 500 degrees Celsius over 25 degrees Celsius gives 61.4%, while real steam plants reach roughly 35 to 45%. Work is precious and heat is comparatively cheap. Separation must be paid for, at 1.72 kilojoules per mole for an equimolar mixture at 298 Kelvin, while real distillation typically uses 10 to 100 times that. Next chapter, we apply delta G equal to 0 to coexisting phases: vapor-liquid equilibrium, Raoult's law, activity coefficients, and azeotropes. Welcome to Chapter 3 of the Chemical Engineering-Thermodynamics series. Chapters 1 and 2 built the two laws. This chapter spends them on a single question. When a liquid and its vapor sit together in a closed vessel, what is in each phase? The title is Phase Equilibrium, and the subtitle is Vapor-Liquid Equilibrium, Raoult's Law, and Azeotropes. Every distillation column, every flash drum, every absorber and condenser you will ever design is sized from the answer to that question. Over the next 10 slides, we will state the equilibrium criterion in terms of temperature, pressure, and chemical potential. Count degrees of freedom with the Gibbs phase rule. Look at how vapor pressure climbs with temperature. Apply Raoult's law to an ideal binary. Read a real temperature composition diagram with its tie line. And finish with the activity coefficients and azeotropes that decide when ordinary distillation simply stops working. Chapter 2 ended with the working criterion of equilibrium. At fixed temperature and pressure, a system moves until its Gibbs energy is a minimum. Apply that to a closed vessel holding a liquid and its vapor, and it resolves into three qualities that must hold at once. The first is thermal. The temperature is the same in both phases, because a hot spot would drive heat flow. The second is mechanical. The pressure is the same in both phases because a pressure difference would move the interface. The third does the real work. The chemical potential of every species must be equal in both phases. Engineers usually restate that in terms of fugacity, which is equivalent but carries units of pressure and reduces to partial pressure for an ideal gas. Fugacity reads as an escaping tendency, how hard a species is trying to leave its phase, so equilibrium is not stillness. Molecules cross the interface constantly in both directions. It is the state where each species leaves the liquid at exactly the rate it leaves the vapor, so the compositions stop changing. Before computing anything, it pays to know how many variables you are allowed to specify. The Gibbs phase rule answers that. F equals C minus pi plus 2, where C is the number of species, pi is the number of phases in equilibrium, and F is the number of intensive variables, meaning temperature, pressure, and compositions that you may fix freely. We write the phase count as pi rather than p so that it cannot be confused with pressure. 3 counts make it concrete. Pure water boiling, 1 component and 2 phases, gives F equal to 1. Fix the pressure and the boiling temperature follows, which is exactly why a pressure cooker works. The water triple point, 1 component and 3 phases, gives F equal to 0. That is an invariant state at one unique temperature and pressure, which is why it serves as a fixed point for temperature scales. Binary vapor-liquid equilibrium, 2 components and 2 phases, gives F equal to 2. Fix the column pressure and the liquid composition, and both the temperature and the vapor composition are determined. That is exactly what a TXY diagram displays. All of vapor-liquid equilibrium is anchored on one pure component property: the saturation vapor pressure. The pressure at which pure species I boils at temperature T, it rises steeply, roughly exponentially, with temperature, because the fraction of molecules energetic enough to escape the liquid is governed by a Boltzmann factor, much like the Arrhenius term in kinetics. Water is the familiar example. It exerts about 0.023 atmospheres at 20 degrees Celsius, 1 atmosphere at 100 degrees, and nearly 5 atmospheres at 150 degrees. That middle value gives us a definition. The normal boiling point is the temperature at which the saturation pressure equals 1 atmosphere. The standard engineering correlation is the Anton equation, which writes the base 10 logarithm of the saturation pressure as a minus b over the quantity T plus C, with A, B, and C fitted for each compound. 2 cautions matter more than the constants themselves. The fit holds only over the temperature range it was made from, and each published set carries its own units for pressure and temperature. Mixing a bar-based set into an atmosphere-based calculation is a classic quiet error. The simplest useful model assumes a molecule cannot tell its neighbors apart, so an AB interaction has the average energy of AA, and BB, such an ideal solution, obeys Raoult's law. The vapor mole fraction of species I times the total pressure equals the liquid mole fraction of I times its pure saturation pressure. In words, the partial pressure a species exerts above the mixture is its pure vapor pressure scaled by how much of it sits in the liquid. Because the vapor fractions must add to 1, summing over species gives the bubble pressure, at which the first bubble of vapor appears. Take benzene and toluene at 90 degrees Celsius, with approximate textbook values of 1.34 atmospheres for benzene and 0.54 for toluene. For a liquid that is 40% benzene, the bubble pressure is 0.86 atmospheres, and the vapor comes out at 0.623 benzene. One equilibrium contact has already lifted 40% to 62.3%. The relative volatility, the ratio of those 2 saturation pressures, is 2.48, and that single number is what distillation design runs on. Here is the diagram the phase rule promised. Pressure is fixed at 1 atmosphere, temperature runs up the vertical axis, and the mole fraction of the light component runs across the bottom. The curves span the 2 pure boiling points, toluene at 110.6 degrees Celsius on the left, benzene at 80.1 degrees on the right. The lower cyan curve is the bubble point curve, the temperature at which a liquid of composition X first boils. The upper purple curve is the dew point curve, the temperature at which a vapor of composition Y first condenses. Below the bubble curve, everything is subcooled liquid. Above the dew curve, everything is superheated vapor. The lens between them, labeled L plus V, is the two-phase region. A mixture landing inside splits spontaneously into a liquid on the bubble curve and a vapor on the dew curve. The horizontal dashed tie line joins that pair at one temperature, here running from a liquid at X equal to 0.3 across to a vapor at Y equal to 0.515, just what a relative volatility of 2.48 predicts. The lever rule then reads the amounts off the same line. The phase lying closer to the overall composition is the more abundant one. The same equilibrium information can be replotted in the form distillation engineers use even more often, the YX diagram. Vapor composition goes on the vertical axis, liquid composition on the horizontal, and the equilibrium curve carries the thermodynamics. For an ideal binary, the whole curve collapses to one expression driven by relative volatility. Y1 equals alpha times x1, divided by 1 plus the quantity alpha minus 1 times x1. Drawn alongside it is the 45-degree line, where y equals x. That line is the no separation reference, because a point on it has vapor and liquid of identical composition. The vertical gap between the curve and the line is the enrichment that one equilibrium stage delivers, and it is precisely the thing distillation exploits. If alpha equals 1, the two coincide, the gap vanishes, and distillation is impossible. The larger alpha is, the wider the gap and the fewer stages a column needs. This is exactly the curve the McCabe-Thiele staircase is stepped off against in Chapter 4 of the companion introduction series. Real mixtures are not ideal, and the fix is a correction on the liquid side called the activity coefficient, gamma. Rayoult's law becomes yi times p equals gamma I times xi times the saturation pressure of I. By construction, gamma goes to 1 as the solution becomes ideal, and as species I approaches purity. Its value carries physical meaning. A positive deviation, gamma greater than 1, means unlike molecules attract each other less than like ones. They push each other out, the pressure runs higher than Rayoult predicts, and a minimum boiling azeotrope becomes possible. A negative deviation, gamma below 1, means unlike molecules attract more strongly through hydrogen bonding or complexes, giving lower pressure and possibly a maximum boiling azeotrope. Ethanol and water is the textbook positive case. Push the deviation far enough and the enrichment falls to 0 at some intermediate composition. Their y equals x, alpha equals 1, and you have an azeotrope, a hard wall. Ethanol and water hit 1 at 1 atmosphere near 95.6 weight% ethanol, about 89 mole%, boiling at roughly 78.2 degrees Celsius. An azeotrope is not defeated by building a taller column. The vapor leaving a stage matches the liquid on it, so an extra stage accomplishes nothing, and no reflux ratio and no column height gets past it. That is why ordinary distillation of a fermentation broth stops just short of 96 weight% ethanol. Industry gets past it by changing the thermodynamics rather than the column, and there are 3 standard routes. Pressure swing distillation exploits the fact that the azeotropic composition shifts with pressure, so 2 columns operated at different pressures step around it. Extractive distillation adds a high boiling entrainer, an added separating agent such as ethylene glycol, which alters the activity coefficients enough to break the azeotrope. Molecular sieves sidestep equilibrium altogether. A 3A zeolite bed adsorbs water and passes ethanol, and that is the standard route to fuel-grade anhydrous ethanol. The lesson generalizes. When the thermodynamics blocks a separation, change the thermodynamics, rather than spending capital on equipment that cannot help. Let us pull the chapter together. Phase equilibrium requires 3 qualities across phases: temperature, pressure, and the chemical potential, equivalently the fugacity of every species, that last one being equality of escaping tendencies. The Gibbs phase rule, F equals C minus pi plus 2, Counts what you may specify. 1 for a boiling pure liquid, 0 at a triple point, 2 for binary vapor-liquid equilibrium. Vapor pressure rises roughly exponentially with temperature and is correlated by the Anton equation, valid only within its fitted range and units. Raoult's law describes ideal solutions of chemically similar species, and the bubble pressure is linear in composition. Relative volatility, the ratio of the two saturation pressures, is the parameter distillation design runs on, and benzene toluene at 90 degrees Celsius gives 2.48. Activity coefficients correct Raoult's law for real mixtures, and positive deviations can produce azeotropes where ordinary distillation stops. Next chapter applies the same Gibbs criterion to species that convert into one another rather than merely change phase. Chemical equilibrium. Welcome to Chapter 4 of Chemical Engineering-Thermodynamics. Chapter 3 asked how matter distributes itself between phases. This chapter asks the analogous question for reactions. Given a feed and a set of conditions, how far can the reaction go before it stops? And what can an engineer actually do about the answer? That is a different question from the one most people ask first, which is how fast? Over the next 9 slides, we build the answer in 4 steps. First, we separate the kinetic question from the thermodynamic question and settle a classic misconception about catalysts. Second, we introduce the equilibrium constant and the relation that fixes it, the standard Gibbs energy of reaction. Third, we work out how the equilibrium position responds to temperature, pressure, and composition, and why the constant itself moves only with temperature. And fourth, we watch those results turn into hardware, in ammonia synthesis, in multi-bed reactors with interstage cooling, and in reactors designed to remove their own product. By the end, you will be able to look at an underperforming reactor and say which limit it is hitting. A reaction is described by 2 independent questions, and confusing them is the most common error in introductory reaction engineering. Kinetics asks how fast. That is rate laws, the Arrhenius equation, and reactor sizing, covered in Chemical Engineering Introduction, Chapter 2. Kinetics governs the path and the time required. Thermodynamics asks how far. Given unlimited time, what composition does the mixture settle into? That is a property of the initial and final states only. It does not care what route the molecules take, how many intermediates exist, or whether a catalyst is present. Which brings us to the blunt statement on the right. A catalyst cannot change the equilibrium composition. It only accelerates the approach to it. The reason is structural. A catalyst lowers the activation energy of the forward reaction, but a catalyst is not consumed, so it must lower the reverse activation energy by exactly the same amount. Both rates rise by the same factor, and the ratio at which they balance is unchanged. The practical consequence: if a reactor is stuck at 30% conversion because equilibrium says 30%, a better catalyst buys you nothing. At constant temperature and pressure, a reacting mixture moves toward minimum Gibbs energy. At that minimum, the composition stops changing, and the standard Gibbs energy of reaction fixes the equilibrium constant. The relation is delta G, standard equals minus RT times the natural logarithm of K, or equivalently, K equals the exponential of minus delta G standard over RT. What is K? It is a ratio of activities of products to reactants, each raised to its stoichiometric coefficient, evaluated at equilibrium. For an ideal gas mixture, the activity is the partial pressure divided by the standard pressure of 1 bar, so K is built from partial pressure ratios and is dimensionless. For an ideal solution, it is built from mole fractions or concentrations relative to a standard state. Take a worked example. A reaction has a standard Gibbs energy of minus 20 kilojoules per mole at 298 Kelvin. K is the exponential of 20,000 divided by 8.314 times 298, which is the exponential of 8.07, or about 3.2 times 10 to the third. So K is roughly 3,200. At equilibrium, products dominate overwhelmingly. Now notice what that exponential does to you. A shift of only 5.7 kilojoules per mole in the standard Gibbs energy of reaction, which is a rounding error by the standards of chemical intuition, multiplies or divides K by 10 at room temperature. Modest changes in delta G standards swing K by orders of magnitude. This is why equilibrium calculations are unforgiving of sloppy thermodynamic data, and why a reaction that should work on paper sometimes has an equilibrium constant of 10 to the minus 6. The sign rules follow. Strongly negative, below about minus 20 kilojoules per mole, gives K far greater than 1 and an essentially complete reaction. Negative gives K greater than 1, products favored. 0 gives K equal to 1, comparable amounts of both. Positive gives K less than 1, reactants favored. Strongly positive, above about plus 20 kilojoules per mole, gives K far below 1 and a reaction that barely proceeds unaided. One caution, this is the standard state value. The actual driving force depends on the real composition, so a reaction with K below 1 still proceeds usefully if the products are kept scarce. K is fixed at a given temperature, but it is a strong function of that temperature. The Van 't Hoff equation states that the derivative of the natural logarithm of K with respect to temperature equals the standard enthalpy of reaction divided by R times temperature squared. Because R times temperature squared is always positive, the sign of the standard enthalpy decides everything. For an exothermic reaction, the logarithm of K decreases as temperature rises, so the attainable conversion falls with temperature. For an endothermic reaction, the logarithm of K increases as temperature rises, so heat helps. This is the thermodynamic root of the statement that raising the temperature of an exothermic reaction lowers its equilibrium conversion. It is not an empirical oddity. It follows directly from the sign. Apply the integrated form to an exothermic reaction of ammonia synthesis magnitude, with a standard enthalpy of minus 92 kilojoules per mole. Going from 300 to 800 Kelvin, K falls from about 4.454 times 10 to the fifth to about 4.333 times 10 to the minus fifth, a collapse of about 10 orders of magnitude. Near complete at room temperature becomes thermodynamically hopeless. Le Chatelier's principle, qualitatively. A system at equilibrium responds to a disturbance in the direction that partially opposes it. Compress it, and it shifts toward fewer molecules. Heat it, and it shifts in the endothermic direction. The quantitative version for gases runs through the change in mole number, delta N, which is moles of gaseous product minus moles of gaseous reactant. K itself depends only on temperature, but the mole fraction composition that satisfies K depends on total pressure whenever delta N is not 0. If delta N is negative, meaning fewer moles of gas on the product side, higher pressure raises conversion. If delta N is positive, higher pressure lowers conversion. If delta N is 0, pressure has no effect on the equilibrium composition at all. Inerts act in the opposite direction to compression. Adding nitrogen or steam that takes no part in the reaction lowers every partial pressure at fixed total pressure, which shifts a negative delta N reaction backward. That is exactly why recycle loops need a purge. For ammonia synthesis, nitrogen plus 3 hydrogen gives 2 ammonia, so delta N is 2 minus 4, or minus 2. Ammonia synthesis is where these rules collide. Thermodynamics gives an unambiguous prescription. Delta N is minus 2, so Le Chatelier says high pressure. The standard enthalpy is about minus 92 kilojoules per mole of nitrogen, so Van 't Hoff says low temperature. Kinetics gives the opposite instruction on temperature. The nitrogen triple bond is so strong that at low temperature nothing happens at a useful rate, catalyst or not. The historic resolution is the Haber-Bosch compromise. An iron-based catalyst, with typical textbook operating ranges of roughly 400 to 500 degrees Celsius and 150 to 300 bar. The temperature is high enough for an acceptable rate and low enough that K has not collapsed entirely. The pressure is then pushed up to claw back what the temperature cost. Even so, single-pass conversion is modest, typically quoted in the 15 to 20% range. The remaining 80% or so of unconverted synthesis gas is separated, with ammonia condensed out and recycled. A reactor with unremarkable single-pass conversion delivers near-complete overall conversion because nothing is thrown away except a small purge. Equilibrium sets the ceiling. Kinetics sets how quickly a reactor approaches it. Design consists of managing both at once, and adiabatic exothermic beds show why that is hard. With no heat removal, the temperature of the bed rises as conversion rises. But we just established that for an exothermic reaction, rising temperature drives K down. So the bed is chasing a ceiling that is falling as it approaches. Conversion and temperature move together, and the equilibrium limit moves against you the whole way. The standard answer is a multi-bed reactor with interstage cooling. React until the temperature approaches the equilibrium limit for that bed, then take the stream out, cool it in a heat exchanger, and feed it to the next bed. Each cooling step restores the headroom that the temperature rise consumed, and the reaction can run again. This is why an ammonia converter is not one long vessel, but a stack of shallow beds with coolers between them. The hardware is a direct consequence of the Van 't Hoff equation. There is one more way to beat the equilibrium ceiling, and it is the most elegant: refuse to let the mixture reach equilibrium at all. If the product is continuously taken out as it forms, the composition never satisfies the equilibrium condition, and the reaction simply keeps running. Two pieces of hardware do this. Reactive distillation carries out the reaction inside a distillation column, so the product is boiled off as it forms. This is standard practice for esterifications, where the equilibrium constant is of order 1 or below, and yet near-complete conversion of the limiting reactant is routine. Membrane reactors do the same job with a selective barrier, typically letting hydrogen permeate out of a reforming or dehydrogenation bed. Excess reactant is the cheap version of the same idea. Feeding one reactant in large excess shifts the attainable conversion of the other. In every case, the cost is downstream: a bigger separation and a bigger recycle duty. That is the recurring trade in process design, and it is worth stating plainly before you reach for any of these. Let us pull the chapter together. Kinetics answers how fast, thermodynamics answers how far, and the two limits are independent. A catalyst cannot move in equilibrium because it accelerates forward and reverse reactions equally, and K depends only on the standard Gibbs energy of reaction. That relation, delta G standard equals minus RT times the natural logarithm of K, means a negative delta G standard gives K greater than 1, and because it is exponential, small changes swing K by orders of magnitude. Minus 20 kilojoules per mole at 298 Kelvin gives K of about 3,200. The Van 't Hoff equation tells you that exothermic reactions lose equilibrium conversion as temperature rises. Pressure shifts gas phase equilibrium toward the side with fewer moles, and inerts dilute and shift it back. Haber-Bosch is the textbook compromise, and equilibrium shapes hardware directly through interstage cooling, reactive distillation, and membrane reactors. Next chapter, everything here assumed ideal gas behavior. At 200 bar, the very condition ammonia synthesis demands, that assumption is simply wrong. Chapter 5 introduces real fluids and equations of state. Welcome to the fifth and final chapter of our Chemical Engineering-Thermodynamics series. Every chapter so far has quietly leaned on one convenient assumption: that gases behave ideally, that pressure times volume equals nRT. Today we retire that assumption. We will look at where the ideal gas law fails, and it fails in exactly the places engineers care about most, at high pressure and near condensation. We will define the compressibility factor, follow the van der Waals insight of 1873, and meet the two cubic equations of state that industrial simulators actually run on, Soave-Redlich-Kwong and Peng-Robinson. We will see how fugacity keeps Chapter 4's equilibrium arithmetic honest at 300 bar. Then we will look at the property package a simulator asks you to choose, and at why that single click quietly decides whether the answer is worth anything at all. From ideal gas to process simulator, Let us begin. The ideal gas law rests on two assumptions: that molecules occupy no volume and that they exert no forces on one another. Both are excellent approximations when molecules are far apart, at low pressure and high temperature, and that covers a great deal of introductory work and a fair amount of real plant operation. Both collapse under exactly the conditions engineers care about most. Near condensation, attractive forces are the entire story. At high pressure, molecules are packed closely enough that their own volume matters. That is not an exotic corner of the operating map. It is the suction and discharge of every compressor. It is the 150 to 300 bar of the ammonia synthesis loop from Chapter 4. It is essentially all of natural gas processing and liquefaction. Using PV equals nRT, there does not produce a slightly rough answer. It produces a wrong one. The standard way to keep score is the compressibility factor. Z equals PV over nRT. Z is the ratio of the real molar volume to the ideal one. Z equal to 1 means ideal behavior, and any departure measures how badly the ideal gas law is lying. Two regimes matter. When Z is below 1, attraction dominates. Molecules pull on each other, so the real gas is more compact than ideal. That is the common case at moderate pressure. When Z is above 1, repulsion dominates. At very high pressure, the finite size of the molecules themselves resists further compression, and the gas is less compact than ideal. Follow methane at 300 Kelvin. At 1 bar Z is 0.998, effectively ideal. At 50 bar it falls to 0.924, an 8% error if you ignore it. At 150 bar it reaches its deepest attraction effect, 0.851. Then it turns, and by 400 bar it has climbed to 1.070, with repulsion dominant. An 8% volume error propagates straight into compressor power, vessel sizing, and inventory. The first successful answer came from Johannes Diederik van der Waals in his 1873 doctoral thesis, work that later won him the Nobel Prize. His idea was to patch the ideal gas law with one term for each failed assumption. The parameter corrects for intermolecular attraction. Molecules pull inward, so the pressure the container feels is lower than the internal molecular pressure, and the term over molar volume squared adds it back. The parameter B corrects for finite molecular volume. Molecules cannot be compressed into zero space, so the free volume is molar volume minus B. Both parameters are substance-specific, and both come from the substance's critical point. What makes this more than a curve fit is what falls out of it. Because the equation is cubic in volume, below the critical temperature it can return 3 real roots at a single pressure. The largest a vapor, the smallest a liquid, the middle one physically unstable. An equation written for a gas spontaneously predicts condensation, a liquid phase, and a critical point. Two descendants dominate industrial process simulation. Soave-Redlich-Kwong, published by Soave in 1972 as a modification of the 1949 Redlich-Kwong equation, and Peng-Robinson, published in 1976. Both remain cubic in volume, and that matters practically. A cubic can be solved fast and reliably for millions of flash calculations, and its multiple roots preserve the vapor and liquid behavior that van der Waals discovered. Both take exactly 3 inputs per pure component: the critical temperature, the critical pressure, and the eccentric factor, a single number describing how far the molecule departs from spherical. In practice, Peng-Robinson is usually preferred for liquid densities near the critical region. Soave-Redlich-Kwong has a long tradition in gas processing, and for most hydrocarbon systems, the two agree closely. Behind all of this sits the principle of corresponding states. Compared at the same reduced temperature and reduced pressure, different fluids behave remarkably similarly. Methane at reduced temperature 1.5 looks much like nitrogen at reduced temperature 1.5. The same equation of state yields more than a volume. From it, you compute each species' fugacity coefficient, an effective pressure correction factor. It is defined so that the fugacity introduced in Chapter 3 equals the coefficient times the mole fraction times the total pressure, and the coefficient approaches 1 as the gas becomes ideal. That is what makes equilibrium calculations survive high pressure. The equilibrium constant from Chapter 4, written there in partial pressures alone, strictly carries a companion factor, K phi, the product of each species' fugacity coefficient raised to its stoichiometric coefficient. In the 150 to 300 bar ammonia loop, that factor is a real correction rather than a formality. These are the same conditions where Z departs from 1/10%, so we should expect nothing else. This is how Chapter 4's ideal gas equilibrium arithmetic stays trustworthy at industrial pressure. Not by being exact, but by being corrected with numbers that an equation of state supplies. Cubic equations of state work well for nonpolar and weakly polar molecules. Hydrocarbons, nitrogen, carbon dioxide, hydrogen, across gas and high-pressure conditions. They work badly for strongly polar and hydrogen bonding liquids, where the interactions are specific and directional rather than an averaged attraction. Water, alcohols, and organic acids are exactly the cases a single attraction parameter cannot represent. For those liquid mixtures, engineers use activity coefficient models instead. NRTL, UNIQUAC, and Wilson are the standard names, with UNIFAC available when no data exists and parameters must be estimated from molecular groups. These models describe deviations from ideal solution behavior in the liquid phase, and they are what reproduce an azeotrope. The practical guidance is short. Polar or hydrogen bonding liquids at low pressure, an activity coefficient model. Hydrocarbons, light gases, or anything at high pressure, a cubic equation of state. Either way, validate the choice against measured binary vapor-liquid equilibrium data. This choice is called the property package, and it is the first thing a simulator asks you for. A wrong property package is the classic silent killer of simulation accuracy. Notice what it does not do. The simulation does not crash. It converges, produces a full heat and material balance, and reports column profiles to 4 decimal places that are simply wrong. Here is the standard example. Model an ethanol water column with a cubic equation of state, and the azeotrope may vanish. Ethanol and water form a minimum boiling azeotrope at 95.6% ethanol by weight, and that is a real physical ceiling on what ordinary distillation can deliver. If the model misses it, the simulator will cheerfully tell you that a modest number of trays produces pure ethanol and hand you a design that cannot exist. The defense is not cleverness. It is data. Regress the binary interaction parameters against measured vapor-liquid equilibrium data for the key pair in your system, and confirm the model reproduces the azeotropic composition and temperature before designing anything. That is routine professional practice, not an advanced technique. Everything in the modern digital layer sits on top of this chapter. A flowsheet simulator is structurally 3 things: mass and energy balances, unit operation models, and a thermodynamic package supplying every enthalpy, entropy, density, and equilibrium constant those models request. The balances are exact and the unit models are approximations, but the thermodynamics is where the physical truth enters, and it is the deepest and least visible layer. A digital twin is a simulation kept synchronized with the operating plant, and it inherits its property package wholesale. A soft sensor predicting a density, a dew point, or a composition is predicting a thermodynamic quantity, and there is a sharp consequence for machine learning. A surrogate trained on simulator output inherits the simulator's thermodynamics, its accuracy, and its errors alike. It cannot distinguish a systematic property package error from physics. It learns the error faithfully, then reproduces it fast and with no warning attached. Thermodynamic literacy is what lets an engineer distrust a simulation for the right reasons. Let us close the series. Chapter 1 established energy accounting, the first law, enthalpy, and the fact that energy is conserved but never free. Chapter 2 added direction and limits through entropy and the second law, why heat flows one way, why no engine reaches 100%, and why every real process destroys some capacity to do work. Chapter 3 applied both to phase equilibrium, the basis of distillation, absorption, and every separation in a plant. Chapter 4 extended the same equilibrium logic to reacting systems, showing how the Gibbs energy change sets a ceiling no catalyst can raise. And Chapter 5 discarded the ideal gas and arrived at the real fluid models that industrial simulation actually runs on. Taken together, these 5 chapters describe what is possible before anyone asks what is practical. Where to go next? Revisit our Chemical Engineering Introduction series, continue to Process-Informatics Introduction for the data layer built on these models, and try Introduction to Bayesian Optimization for deciding when each experiment is expensive. Thank you for learning with us.